Hello everyone, in this video we'll be solving problem 63 unique paths part 2. The problem statement is we are given an m by n integer array grid with some obstacles in it. We need to calculate the total number of unique paths from the starting point to the last point. We are only allowed to move in two directions, either downwards or towards the right. Let's look at example number 1 where we have a 3 by 3 grid. In this example, there are a total of two unique paths to reach from the starting point to the ending point with those two directions given to us. One is to move towards the right and then downwards, and the other is to move downwards first and then towards the right. Both of these paths do not include any obstacle cells in it. The problem statement is very easy to understand, and so is the implementation if we consider the brute force approach. Let's switch to whiteboard and discuss potential solutions. Let's start by discussing how we can use brute force approach to solve this problem. In this approach, the idea is to explore all possible combinations we can build from each cell that can help us reach to the last cell in the grid. Considering the first cell that is 0, 0, we are allowed to go in downwards direction or towards the right. In other words, we are trying to build a decision tree where the current cell will be the parent with two children. One will be the cell to its right and other will be the cell to its right bottom. We will continue to build the decision tree until we reach the last cell in the grid. For traversal, it will be ideal to use a DFS based as it will help us identify all possible combinations and then reuse it if we encounter the same cell again. During the traversal, if we encounter an obstacle from the original grid, we'll stop traversing through that particular leg and try the other one. With this solution, our time complexity is going to be exponentially high because we are processing the same cells multiple times as part of different paths. One way to improve that is to use dynamic programming array into our solution. This dynamic programming array will be used to store the values of all unique paths from the current cell to the last cell. So if in case we encounter or run into that same cell again as part of a different path, we can avoid calculating it again and do a simple lookup. With this improvement, our time complexity is improved to O of m into n, where m and n are the number of rows and columns given in the grid. While the space complexity is also going to be O of m into n, as we are using this additional collection to improve our time complexity. Now let's discuss if there is an optimization that we can do to improve our space complexity. Before we dive into the optimization, let's do a quick dry run using the previous approach. Let's say the starting cell is x and the last cell or the destination is y. The total number of unique paths for x to reach y is going to be the addition of the value at a, which is the cell to its right, and b, which is the cell to its bottom. It is because these are the only two directions we can move. Similarly, the total number of unique paths from a to the destination is going to be the sum of the cell to its right and the bottom. And because the cell to its bottom is an obstacle, we'll consider it as 0 and only take the cell to its right. I hope this logic was clear in understanding how we'll be approaching and solving the problem. Now let's start by using some numbers to get a better idea. The last cell or the destination that we are trying to reach will be having the default value of 1. As we were talking about using a DFS based approach here, we'll start with the last cell and move towards the starting point. There are two directions to reach to the last cell. One is from the top, another is from the left. The directions are reversed because we are going from destination to source. For the cell right above the destination, the total number of possibilities is going to be the sum of the value of the cell in the bottom and towards its right. As there are no cells to its right, we'll consider that 0, so the current value will be 1. Applying the same logic to the cell on the left hand side of the destination, adding the two values will be 0 and 1, the sum is 1. The same logic will be repeated for all of the cells in the grid until we reach the first cell, that is the source. When we are looking at the starting position, the sum of the values of the two cells to its right and the bottom is 1 plus 1, giving us the total 2. This is what we can return as the output, as it tells us there are two unique ways of reaching to the destination from the source. And because we were using this entire collection to store the unique paths for each of the cell and building on top of it, our time complexity is much better. Now let's discuss the improvement that we can do to this solution. When we are calculating the value of any of the cell, we are only using the value of the cell that is to its below and to its right. We do not need any of the other cells for calculation. In other words, I only need the value of the next row to calculate the value of the current row. And once I have calculated the values for the current row, I can discard the previous row and replace it with the current row. Let's use the same example to understand this approach. I will start by calculating the value for the last column in the second last row, which depends on the cell right below it and the cell on the right hand side, which does not exist. So technically we are only going to be using the value that is saved in the previous row. After using the value of the last row and last cell, we don't need that cell anymore. None of the other calculation that we will be doing requires that value. The same logic can be applied for the remaining cells in the last row. We don't need to use those values once we have calculated the corresponding column value in the previous or the second last row. So instead of using a new collection to store the values of the second last row, we can simply replace it into the last row directly using in-place operation. This approach will help us reduce the overall space complexity from O of m into n to O of n, where n is the number of columns. This improvement does not impact or change the overall time complexity, it only improves the space complexity. I hope you are able to understand this explanation. Let me show you how we can implement this using C#. In this C# implementation, I start by adding a validation to make sure that the length of the obstacle grid given to us is greater than 1. If not, then I'm returning 0 as the output. After that, I'm initializing a dynamic programming array of type integer and setting the length to n, which is the number of columns. By default, the first element in the dynamic programming array is set to 1 as it is the starting point. After that, I'm starting two nested for loops to iterate through all of the cells in the given grid. If the value of the cell that I and j pointers are pointing equals to 1, it means it is an obstacle, so I'm setting the corresponding value in the dynamic programming array to 0. Else I am checking if the value of j is greater than 0. If yes, it means there is an element or a cell to the left hand side of the current pointer, so I can use that and add it to the current value of j and save the sum into the jth position in the dynamic programming array. After the for loop is complete, I am returning the last value in the dynamic programming array as the output. This code, when submitted on LeetCode, beats 100% of the submissions in terms of runtime and nearly 56% in terms of memory. Thank you for watching this video. I hope you are able to understand the explanation. The details to access the source code is available in the description below. Feel free to check that out and I will see you in the next one. Thank you.